very happy to have Dear Lee come to give us this colloquium. Dee is, of course, the chief scientist of the radio astronomy division of the National Observatories of China, as well as the deputy project engineer of the FAST telescope. He obtained a PhD from Cornell and held positions at the CFA in Harvard, and as well as many of you will probably remember him from his time at JPL between 2005 and 2011. Dee has worked extensively in galactic and extragalactic ISN at both radio and infrared wavelengths, but has sort of really impressively branched out to a bunch of other things now, with adding pulsars and fast transients to his resume as well. And so he's going to tell us about the Commensal Radio Astronomy Fast Survey, or CRAFTS, as well as other very exciting discoveries being made by the FAST telescope. So please, Dee, take it away.
Oh, thank you. Thanks, Greg, for the nice introduction. Let me try to click on the this meeting is being recorded warning. It's kind of on my screen. Just 1 second. Continue. All right. So as you can see, this is my latest trip to FAST, and it's like a virtual background, but let me assure you it's real. So this is the Chinese name for the FAST telescope, and it is the English. The acronym comes from the 500-meter Aperture Spherical Radio telescope. So it's really in terms of acronym goals, this is quite honest. If you look at the image, this was taken in 2016, just a couple of months before first light. And you can see the spiral of the light, which is a semi-truck driving underneath the dish. So when you look at the dish, you actually look at a semi-translucent structure, because more than 50% of the area are actually empty. They are made up of holes about 0.5 centimeter in diameter, since it's much less than the working wavelength. So it's still an efficient reflector. And right now, it is the largest single dish antenna in the world. As a project, it was first proposed in the middle of 1990s as one of the competing concept for SKA, sort of large dish, small number concept. But later, it became a standalone project. And in late 2007, it was approved by the funding agency, and the construction started in 2011. And in September 2016, we got first light. And after 3 years of commissioning, January of this year, we transit into normal operation. So on September 25th, the Vice Prime Minister, which is the lady in the first row, came on site to read a congratulatory letter from the president of the country, which I written here in Chinese, but it can be rigorously translated into publish, which is what we're trying to do here. So we have many collaborations, and one of the more active and fruitful one is with Sandy Warnrep in Caltech. So on the right is our chief engineer for the receiver group, and he came to Caltech in 2010, and we have this nice chat on campus in front of the cafeteria. And I started as a project scientist for the project ever from its funding being approved in 2007, but I only start work full-time for the project in 2012. And by that time, Sandy's group has successfully demonstrated the capability of the quad-bridge ultra-wideband feed design. So I proposed this concept to the engineering group and Dr. Nan, who was the chief engineer at the time, and it was a rather quick and cheap project. In addition to the 7 set of receivers that was approved in the original plan, engineering plan, we also added this ultra wideband feed, which actually provided the first slide and shoulder march of the commissioning task. So it's uncooled. It has 60 to 70 Kelvin system temperature, but it worked really quick and does a wonderful job. There are many engineering challenges for the project, so I just list one here as a demonstration. So one of the rather unique aspect of this telescope is that its focus has no solid connection to the ground. It's only hoisted up and move around by 6 very thin cables, and the cross section of those cables are 4.6 centimeters. So look from the scale of 500 meters, it's really hardly perceptible. So that does give us a very clean beam. It doesn't block the aperture, but on the other hand, things like optical fibers doesn't really like to be sort of dangling in space. Usually it's either buried underground or in some structure. So that requires special fibers that can sustain bending and repeated stretching. So that's now a proprietary technology we developed together with the industry. So probably most of you are familiar with Arecibo, which sitting stationary, that has a stationary primary, but it has a rather complex secondary and tertiary mirror hosting in a big dome weighted 300 tons. And the concept of FAST is still use primary focus. So it's a simple dome, only 30 tons, but has active primary. So by shaping, basically changing the tension distribution in the primary, it can change in real time 300 meter of this 500-meter dish from part of a spherical cap into a parabola. So in doing so, it can cover 40 degrees from Venus and can track and can also do scan. And this was a video I shot in 2018. And now we can lift the dome in a couple of minutes and flying around, and not only flying around, but locate it to a precise location and tilt in 3D space down to 1 centimeter, just using those 6 hardly visible cables. And if you can look through the dish and look underground, there's hundreds of thousands of fibers that just transmit signals and command back and forth. That 4,500 panels and driven by 2,000 and a little more than 100 actuators in real time. So it's a rather complex engineering structure, and the total budget, final budget, is about $170 million. Just to put things in perspective, we were located in the poorest province of China, in Guizhou, and in the nearby region of our location, there used to be just villages with relatively little population. Now, in the nearby town, there are 2 5-star hotels, and the construction cost of those 2 hotels rival the full cost of the project. So I always call it a really cheap mega science facility. And this was a graph made by Mary from Max Planck. So everything here was are to scale. So we can literally put Effelsberg Green Bank parks and Arecibo into the depression that holds fast. And we cover about twice the sky of Arecibo and has about 2.5 times more beams in terms of focal plane array. And that also aided by the twice to 3 times the absolute sensitivity or gain. We have roughly 10 times the surface speed of Arecibo. So that represents a significant advance. The original, and I think it's largely still hold 5 primary stated science goals. This 21-centimeter line, there's pulsar, molecular spectroscopy, VLBI, and SETI. So pulsar and H1, that still are the bread and butter of this concept. After first light, it takes us about 8 or 9 months before we can confidently start to detect pulsars. So this is the first new pulsar confirmed. It's a normal pulsar of a period of 1.8 second. It was publicized on October 10th, 2017. Since then, we really have been on track to be the most productive sort of pulsar discovering machine for the current era. And of course, not all pulsar were created equal, and we are very much in debt to the great Don Becker, Sri, and our dear friend Carl for the discovery of millisecond pulsar, which is nowadays being widely used for testing gravitation theories and try to measure the low frequency gravitational wave. So we have our first millisecond pulsar discovery in 2018. It was a targeted tracking observation toward one of the unassociated Fermi sources. And then we send our ephemeris to the Fermi team, and they also folded the Fermi archive. They can get a very nice gamma ray photon profile and can actually do timing on it. I was really impressed how much you can do even with the small count of high energy photons. So a paper is in press. It should come out soon. So this is in 2019, we published our first APJ paper, so international journal paper. This is of the so-called C12. It's the 12th pulsar that we have confirmed. It has a plethora of emission phenomenon, has nulling, mode change, and it seemed to be intermittent. And there's some relatively strange behavior, like one of the pulse component in phase seem to always turn off first for the last pulse before the nulling. And so I won't go into details here, but the last sentence of the abstract, which was accepted by the referee, says such a pulsar pose challenge to the classic carousel model. So I was not as Vikram has introduced. I was largely trained in ISM and radio observation, but and one of my thesis committee member is Jim Cordes, but I was never really too fluent in terms of pulsar speak. So I got really excited. I was about to putting in much more time on this source until Dick Manchester told me that almost every detailed studied complex pulsars with complex phenomena challenge that classic model. So that just show how much that we are still largely ignorant about the detailed emission mechanism of pulsars. And we also have special issues on the Journal of Research in Astronomy and Astrophysics, and the other journal, the so-called Science China, Physics, Mechanics, and Astronomy. So they discuss both our commissioning result, the new measured sensitivity, and also give so-called quantify the science potential of FAST in certain areas. That's from the IOP website report. So that's including of measuring fundamental constant with masers, cosmic rays, exoplanet, gravitational wave, magnetars, and interstellar medium, and so forth. So back to our primary goal, in terms of H1, it's really a sort of a foundational science. So every 10 years also, the radio astronomy community will produce a very large area H1 sky survey that serve as a basic input to many of the other domains. And the golden standard right now is the so-called the Leiden, Argentina, and the Bonn survey, which cover the whole sky with 36 arc-minute resolution, and it's widely used. It's both published in paper and also has a standalone book. And the one of the key features is that it has absolute flux scale, and for all the sort of improved survey following that, there's one HIFO-Pi from Effelsberg and Parks, and also Galfa from Arecibo, which I was involved early on, tie the flux scale of the H1 image to lab survey. The so-called high-FAST survey from FAST hopefully will cover the full northern sky, a little more than 2 pi. So it's about 57% of the full sky, but with its own absolute scale. So that should represent the next major generation H1 survey. And to do H1 survey, you really have to calibrate the short-term the gain drift. So the gain can change on second time scale, particularly electronic gain. For example, any temperature fluctuation will result in different performance of the LNA. It can be just 1% or even a fraction of a percent, but it's very perceptible. So this is Arecibo. You can see those scan drift. This is a post processing step. So to enable sort of such images, what H1 astronomers do is to inject electronic noise before the LNA, and you inject it, say, at 1 hertz. So once every second, since you know you can calibrate the strength of that electronic noise and use it as a secondary calibrator to calibrate out the short-term drift of the gain. But the pulsar folks hate it. The reason pulsar folks hate it is that if you have a 1 hertz injection, then you Fourier transform it into power spectrum, you will have a 1 hertz signal, and then you have 2 hertz, 4 hertz, 8 hertz, all the way down to the higher orders of harmonics, and all those are much stronger than any of the new pulsars you are going to search in the power spectrum. So so the pulsar folks, when they do pulsar search or pulsar timing, at most they will fire a cal before the observation, then they just turn it off. Also, pulsar is a characteristic signal in time domain, so at least on the first go, people don't care about the absolute flux. It's scintillate anyway. So ever since 2015, through the collaboration with Dan Wurzenheimer, who was the founder of both SETI at Home and the Casper Consortium, I realized that right now the processing capability of modern digital backend has progressed such that in principle, we can solve this cal problem by inject the cal really quick. And this concept was finally realized by my sort of junior academic sibling from Cornell, Dr. Mark Kirchhoff. He is now a senior staff in NAOC. So what we did is to inject the cal at the sampling speed. So that's at about 50 microsecond or 100 microsecond. So we inject the cal more than 10,000 times every second. Then if you Fourier transform it, all the power will be in the even higher frequency, so time frequency domain. And right now we don't know any sub-millisecond pulsar. So it's safe for any of the pulsar types we know. And this is rather straightforward concept, but it rely on the modern digital backend that combine the processing speed of FPGA and GPU, and also there's a lot of details to work out the fiber lengths. You try to sync the signal. So Kirchhoff has worked almost 3 years on it, and it's right now it's worked fabulously. So based on this mode, we and the 19 beam focal plane receiver, so-called FLAN, how fast we designed this drift scan survey that we can rotate the feed, which has a one beam width gap between each feed to a certain angle, and then stacken them up. So each stripe is about 20 arc minute in DEC, and then we end up with 19 evenly super sampled stripe on the sky. And it will take more than 500 hours to cover the full northern sky. And it's so-called Commensal Radio Astronomy Fast Survey. Again, as the acronym goes, it's rather unimaginative, but it's easy to grasp. CRAFTS would represent the first Commensal survey of pulsar, H1 galaxies, H1 imaging, and transient. And basically, we observe once, and we separate the data stream into 4 backend, and they will process the data semi-independently, because the H1 data will have to rely on the pulsar data to extract the cal signal and calculate the T-sys and apply it to the spectral data. And this concept was described in this IEEE journal, and you're welcome to take a look. So one of the immediate challenges is the data rate, and it's dominated by the pulsar data. So it's roughly 6 gigabytes per second, and which is faster than the normal hard drive. So you can now even write on a hard drive without doing some parallelization or some combination of the solid state drives. And it's also quite costly. So right now, what we do is that we have this on-site infrastructure that with the help of Ali Cloud, and we use a combination of Kubernetes and Redis and some GPU processing to basically connect it to the backend to compress it either to 2 bits or 1 bit. And in addition, we summarize the parallelization. So the final total product is about 1 petabyte per year. It's still costly, but it's rather manageable. And in terms of the major science of the CRAFTS survey, one of them is to give a census of the H1 galaxy in nearby universe. So on the left, this is a paper, a summary paper of the Arecibo, the so-called Alfalfa survey. They have more than 30,000 galaxies, the largest sample by far of H1 galaxies. But only those sort of shaded area are complete. So they are only complete even in the low redshift beyond 10 to the 9 solar mass. And the comparison between the optical galaxy and H1 galaxies actually become interesting right around 10 to the 9. So you really want to go into 10 to the 8 and or a few times 10 to the 7 solar mass regime. This is what FAST will do. So this is a published estimate. There's a comparison between alfalfa and the expected detection of crafts in blue. So we expect a sample of more than 500,000 H1 detections with a median redshift of 0.07. So that represents 1 order of magnitude progress if we can realize that. This is just something I'm personally working on. It's simulation largely done by Tapper Garcia and Josh Bland Hawthorne from Sydney University. We utilize the current fantastic proper motion measurement from Gaia 2 of M31. So this is the look back history of the interaction between M31 and M33. And it has a close approach, as close as about 30 kiloparsec, about 6 giga-years back. And also it's currently it's in the close, the second close approach. And the interest lies in that out of the simulation that we not only predict there is a connecting gas stream, sort of relics from the interaction, but there's also trailing gas stream, trailing M33. So this is rather interesting. I think there's this famous paper from Robert Brown that first detected the gas in between M31 and M33. And then GBT further resolve this gas into rather discrete clumps. But the question still remains that whether it's a tidal interaction stream or is part of the baryonic halo of M31. So I think by actually getting a much deeper and more complete picture of this gas, FAST has a potential to resolve this question. So H1 imaging turns out to be much harder than discovering pulsars. Since for the pulsar is a time domain signal, we do Fourier transform, do the dispersion trial to try to look for the signature in the power spectrum. But for H1, you really have to calibrate the scan pattern, the gain drift, and the stray radiation and whatnot. So on the left is the GBT image of the Lockman hole. On the right is our 2019 result, and this is our 2020. I think we are getting very close to publication quality. So one of the characteristics of the draft survey is that in, say, a 24-hour full scan, we can detect about 500 continuum sources, the majority of which are quasars. And this grid of quasars actually provide us a calibration sort of anchor. And then we can further anchor that to the VLA stable quasars. There's only a few, very 3C 279 and 3C something, that then we can really build up sort of wave a grid that we can have a very good absolute flux calibration. We are just only halfway there. So on the right is a strip scan past a quasar. On the left is a continuum image of a supernova remnant. In the middle is a polarized flux. So it's still require major improvement, but in concept, we can get there. So this is a summary of the large coverage pulsar survey. So the reddish thing is the Arecibo drift scan survey, And also there are a bunch of galactic plane survey from Parkes and also LOFAR and GBT. So this is the expectation for the FAST survey. So it should cover all the area between those two solid red lines, and the contours are expected new detection. So they concentrated into the onto the galactic plane right outside of Arecibo sky. So it's either to the south or north of the Arecibo coverage. And this is the millisecond pulsar. So you can see the expected millisecond pulsar discovery has a higher scale height, since they are older so-called quote-unquote recycled pulsar. So they tend to travel further away from their sort of natal birthplace. And right now we know about close to 3,000 pulsars now, the majority of which are radio pulsars, and the FAST should about double that in the combination of surveys. So this year we published our first systematic follow-up timing paper. So it's 11 pulsars we discovered using the ultra wideband feed, but the timing was done by the Parkes telescope, which has a more mature timing system. And this was led by Andrew Cameron from NLC and jointly from CSIRO. So from the CRAFTS survey and the later follow-up timing, now we have actually close to 20 binaries, and about 10 of them we have solved the orbit. And one of them is a double neutron star system. We're still working on the Shapiro delay and other more physical aspect. So for confirmed discovery, we publicize on the CRAFTS website. This is the PP dot diagram. So you can see all the pulsars. So the normal pulsars, the triangle are the magnetars, and so the red solid star are the pulsars that we have a timing solution. So that's about little less than 30 of them, and some we only have upper limit. And right now we actually have more than 120 confirmed discoveries, including 40 millisecond pulsars and binary. So we are on track to meet one of the expectations is to contribute potential millisecond stable timers to the PTA effort. And this is just a semi-analytic calculation of expected supermassive black hole binary population from redshift 2 to the current epoch. And the locus of the expected gravitational wave from those supermassive black hole binaries has from the higher redshift, the lower redshift will increase in frequency, but collectively they will drop in the magnitude or the strain, and then will further increase once really get to local. So the gist of this recent paper is that for SKA sensitivity, you don't really need to monitor 1,000 MSPs, but you only need to monitor for decades, say 20, 30 very high quality MSPs, and that will allow a detection of a single source within 5 years. And with 10 years, from 10 years on, there will be about 100 new so-called continuous or single source detection every year. So that would really open up the field of study of supermassive black holes through PTA. But that's at least 30 years into the future. So anyway, so this is a summary of all the pulsars that have been either published or announced So you can see the Monoglo and Arecibo, they are major contributors, but since the middle of 1990s, the field was being dominated by Parkes. And FAST, or rather Craft survey, come into play from 2018, and it's a much more diverse field now. So there's LOFAR, there's Fermi, and there's GBT and Arecibo still, but FAST will be a leading or one of the major players. And so with the Craft survey, we of course are very grateful to Duncan, who gave us the Lorimer burst in 2007, although at the time nobody really believed him. And since 2013, the fast radio burst really become a very active field. And Xiaomi Chatterjee from Cornell published the first localized fast radio burst and really ascertained its extragalactic origin. So this is a major development. So we did, at the time in 2016, based on only 20-some fast radio bursts published at that time, we did a quick estimation. So even with the 19 beam, our detection rate of about 5 per 1,000 hours is really not competitive with the chime or even ASCAP. But we do have a unique depth. So if we can follow up known locations, we can detect fast radio bursts up to redshift of 10 if they exist at that higher redshift. So that's what we start to do. One of the major development is this AI single pulse infrastructure on site built by Weiwei Zhu, and we are still working on that. So this year we have published our first new FRB from the blend search of the Craft survey. It's I think it's either ranked at the time ranked either the second or the third in terms of dispersion measure. So it has an expected DM access redshift close to redshift of 2. It has a triple peak structure, so it looks like one of those repeaters, but we haven't been able to catch its repeating. So in the data we accrued so far, we only processed so far up to the end of 2019. So these are the 3 new discoveries. So they collectively tend to have higher DM. And this is a new repeater. It was detected in data from 2019, May 20th. And since it's a drift scan, and we even in the first drift, we see multiple bursts. So we see 4 pulses in 10 seconds. Not only that, since it's a drift scan and have multiple bursts, so we can roughly localize it to the size or slightly better than the size of the fast beam. So now in the follow-up this year, we have detected close to 100 pulses. So it's really active, and it doesn't seem to turn off, unlike 121102. So then, with the help of the real fast team led by Casey Law and Xiaomi Chatterjee and Sarah, we were able to localize it with VLA on July 21st this year. So the localization now is being improved with further multiple detections also into higher frequency band. That enable us to get a optical redshift from Palomar. So the observation, the data was taken by Dan Stern and the effort led by Chaowei Cai, who is also who used to be a UCLA and JPL alumni, and now it's a staff in NAOC. And further effort is to get a optical image and better characterization of the of the host galaxy, and that's an effort led by Chris. So this is just a very incomplete list of collaborators. So we have a pulse detection at fast VLA, redshift, the spectroscopy at Palomar, and pulse detection at VLBA, GBT, and recently at Parkes at between 2 to 4 gigahertz, and non-detection at EVN and Effelsberg, and hopefully we can push it further. So I think one of the key characteristics of this source is that it has a DM redshift estimate somewhere around 1.2, but the redshift measure is only 0.2. So it's very much like 121102. The burst source seemed to be shrouded in local electrons, and we can also see the hint of scattering. So this will very much further constrain the origin of fast radio bursts. So since 2019, we have also installed a dedicated transient backend. So it's the same hardware, but has two software, one for SETI, one for fast radio bursts. So they are processed differently. Since for SETI, you want like more than 1 billion channels, but you sample it at every second. And for the channelize it at every second. For fast radio bursts, it's built on the Handle pipeline and try to do real-time detection. So in the first field test, we managed to catch the active phase of 121102 toward the end of August of last year. And then we had a continuous campaign of little more than a month. And within less than 50 days, we got more than 1,600 pulses from this one source. And that represents about 5-fold increase, more than the total sum of detection of 121102 from all other instruments in the last 7 years. And it's become immediately obvious that it's fast radio bursts cannot be a catalytic, say a neutron star merge or anything like that. Since you can see that there are 2 days, one in early September, another at the end of September, it has a overlay rate more than 100. So it's really like a pulsar, and it's just bursting away. And this is the de-dispersion effort. So in this little animation, I'm just changing the dispersion measure by 1,000 of the total DM. You can see the profile will dramatically change. And then considering you also have different sensitivity threshold of different telescopes. So it's really a cautionary tale that it's very hard to get the profile, the arrival time, number of bursts accurately for a isolated burst. So what do we do is that if we, in a certain day, in any given day, if we have multiple bursts, we will try to get a reasonable look, right? To try to get it all looks straight and within a certain range. So I think that gives us a more robust DM estimate. So the median, the median DM of all 1,600 bursts is 566.7. It has a large scatter. The scatter is about 6, but in combination with all the previous detections from the 7 years, the DM seem to be increasing at a rate of 0.85 per year. So who knows? But it can be explained by supernova remnant. So this is the count, the energy distribution. So it's not a power law by any stretch of imagination. It's clearly a bimodal distribution. So if the previous explanation of power law is just an artifact of the sensitivity. So if you only look at the high energy or the bright part, then you can approximate it by a power law. So this is the burst rate. So it's a little bit more physical here. So we have a burst energy across about 3 orders of magnitude and the hourly burst rate, and we can really fit this by a function, a combination of a log normal plus a Lorentzian function. And if we look into the sort of the goodness of fit, you certainly cannot fit it by a single power law. You cannot fit it by a single log normal. I mean, it's pretty obvious. So what happens is that we think at the low energy end, the log normal represents some underlying stochastic processes. I really cannot say any more than that. And on the high energy end, the Lorentzian function is a steepening power law, meaning that you get lower probability than a single power law when you go to higher and higher energy. And a Lorentzian or a Cauchy function is actually the distribution of the overlapping area of 2 independently distributed Gaussian. So it may represent some coherence mechanicism. And the only reason it was only discovered or realized now is because of the sensitivity. So the characteristic peak energy, about 5 times 10 to 37, is right on the detection margin of Arecibo. So none of the other telescopes can even see it. And the Parkes detection threshold is marked, it's way to the right. So if you have a combination of the higher detection threshold and the lower sampling number, you will tend to get a power law. So this is the pulse width distribution of the Crab giant pulses. So again, it's a log normal distribution, roughly peak at 10 microsecond and has a characteristic width. And this is the pulse width distribution of 121102. So it has a peak about 3 millisecond effective width, and also a log normal tail. So it's roughly just a scale up of the giant pulses from Crab by a factor of more than 100, and in terms of the pulse width distribution. So we have to do a very rigorous periodicity search. We can rule out any periodicity, rigorous periodicity between 1 millisecond and 1,000 seconds, beyond which we have no sampling. And the characteristic peak of the waiting time is about 4.1 seconds, but that has been demonstrated as purely a sampling. Since we say we observe 1 hour or a couple hours every day, then if you just randomly threw, say, 1,000 point or 2,000 point in there, you would tend to get that characteristic waiting time peak. However, there's another peak at about 3 to 4 milliseconds. So that one is real. That basically demonstrates there are some very closely spaced together pulses. When you have very strong pulses, you tend to have multiple peaks. That's what that is. So that waiting time peak is different from Arecibo, from the sample of 41 bursts. But that 41 bursts, I'm pretty sure is also consistent with random sampling. So at least at the moment, this one repeater, in terms of time domain, it looks white. So this is just some of the plot on the top, and the first row and second row we did Lambsgargo. We also did FFT, and we also try to do straightforward folding. So only significant peak is close to 1 day. So that's a artifact of this observation, since we take data every day and almost in the same range of our angle. And I think we pretty confidently rule out any straightforward periodicity and even any QPO of 121102. So there is this published long-term periodicity about 156 days, and adding in our data, keep in mind that the fast data things only space over little less than a year. So although it's a very large number, it doesn't really add too much in terms of the sort of certainty of this long-term period. But the bottom line is that add in all the fast pulses, that period peak is still there, and it doesn't reduce its significance. And also we start to get new detection this year. So the yellow area are the predicted active period, and the red dots are the dots are detected pulses, both from Effelsberg and fast, and those a little square to the top are when we take data. So at the moment, it seems to be that long-term period seems to be still hold. But yes.
About 5 minutes to go.
Okay, all right. I'm almost done. So out of crafts, there could be also other transient. So one of the more interesting one is from exoplanet, which has never been in radio band, has never been conclusively detected, but there is brown dwarfs that could have a similar mechanism. So this is a seminal paper from Greg, and we recently did a prediction. So in the craft survey, we should be able to catch a few hundred of bursts from brown dwarfs. And so this is the summary of the craft survey. We aim at 1,000 new pulsars in drift scan, about 500,000 new galaxies, 10 billion voxel H1 images, a few tens of new fast radio bursts, and all this seem to be on track, but we are just at very early stages, and maybe some other strand transient. So we just closed our first call for proposal. The over subscription ratio is about 4.5 to 1, and roughly sort of equally grouped into 6 categories. And next year, now we are certain that it will be open to the international community. The fraction is still being negotiated, but so anyone from Caltech can, if you are interested, can be PI of past proposals. So I will, I'm just reading a book, this fantastic book by Martin Harwood. It's In Search of the True Universe. It's so great. It's a rather personal but comprehensive view of the development of astrophysics in 20th century. So, for example, here it lists 14 unexpected major discoveries, only 2 of which from optical. I guess it's just the optical astronomy is just rather relatively more mature, and then it's from X-ray, infrared, and radio band. And so that's figure 9.2 from this manuscript. It's demonstrate in concept that astronomy, which largely sort of lead by observation and major discoveries, is made feasible by infusion of technology. So with the gamma ray detectors and that military monitoring satellite, there's gamma ray burst, which is open up a totally new field. So I just, by the power of Photoshop, I add fast radio bursts there, and it's right now it's really a active field, and we have many experts in Caltech, and we have this very active collaboration with Casey and with Chris. And I just want to close by one of the first sentences from this book, which really leave me a very deep impression. What Martin says is that when he was a grad student, Einstein was still alive. So everybody wants to be Einstein. And in the special relativity paper, there's no reference So that leave a wrong impression that sort of Einstein just made up elegant theories out of the mathematical consideration and just physical insight, which is not true. Einstein well versed in, at that time, the experimental and philosophical and scientific considerations, and not the least of which is principle. So what Martin says that if he has one wisdom to part with graduate student, if we can go back to his graduate student year, is that science is a craft. I'm a true a believer of that, and I hope the craft survey from FAST can be part of the progressing craft of radio astronomy. So thank you.
Awesome. Thank you so much, Steve. We have a few questions that are already lined up.
Okay.
But just quickly, if anyone else has questions, please either raise your hand or type it straight into the chat. First is from Mansi. So Mansi, I think you can unmute yourself.
Thank you so much for that excellent talk, Dee. I just have a quick question. I was amazed by that histogram that you showed that spanned 3 orders of magnitude in energy for your fast radio burst detections, repeaters. So I was wondering if FAST has actually stated that a localized FRB had not seen any repetitions. I mean, can it sort of make a definitive statement on there being 2 classes of FRBs? Because with your exquisite sensitivity, if you don't see any repetitions for a very long time, then that must be
right. Right. So at the moment we cannot. It's just that the number of discoveries, new discoveries, only about 5. So I think such a statement can only be made when CHIME releases like 1,000 discoveries. Then we can do a more systematic follow-up. Things right now we are doing blend search, and then we can only go back to try to catch a repeater, and right now we only have 1 new repeaters. But if I were a betting man, I would more like to bet that if not all, but most of the FRB may be repeating.
Thank you.
But that's start to get into the non-scientific sort of belief regime. Sorry.
All right. Thanks, Dee. Okay, next is Wenbin. Can I please ask the questioners also to turn your video on so we can see you?
Vikram, just in the chat window, I think Shri, Greg all have requested.
Yes, yeah. I've got them lined up. There's a list. Yeah, Wenbin, go for it.
Oh, so I have 2 questions. So one of them is on the same slide. You have this energy distribution, which is beautiful, with so many bursts. I wonder if you can cut all your bursts in 2 halves. Let's say the first half in time, if you see the same distribution in 2 halves. Has that been done? So that's my first question. The second question is really simple. It's just 1 sentence. It's for this repeater 1905-20. You said the DM was largely contributed by the nearby medium because the redshift is too low, like 0.2, whereas the total DM is pretty large. Do you see, because you have seen multiple bursts, do you see a DM evolution from that particular burst? That's all.
Uh-oh. Hang on, I think.
Sorry, I only heard the first question. I will reshare. So Wenbin, can you repeat your second question?
The second question was on the 1905-20, the other repeater, which was localized to have a low redshift at roughly 0.2, whereas its DM is very large.
Yeah.
So which means that most of the DM is contributed by the local That's what you guessed. So if it is really from the local, do you see a time, like a temporal evolution out of your repeating sample?
Right. Okay. So the first question, the answer is that no, I have not done it rigorously, but my educated guess that if we cut the time in half, it will still have this this distribution. Things that there are certain days we tend to see a lot of more bursts, but the bursts will cover a full range of the energy. But that's an excellent suggestion. We can with this number we should certainly explore that. For the second question, the only thing we have looked at about that 100 burst compared to 2019 is DM seem to be dropping. But keep in mind that it's very hard to get an accurate DM. So on any given day, the range of reasonable DM are a few, and so that's a counter example to 12-11-02. But I think even for 12-11-02, there are some people have the suspicion is that increasing trend was largely anchored by the first point.
Yes.
And the way of fitting DM has evolved, and I really cannot go back to get that original point. So I think this is a very interesting and important aspect. But even at that changing rate, that's only about 2,000 of the DM per year. It probably will require at least a few years, and preferably of the same instrument and the same technique, and to get that trend be more robust.
Thanks so much. Thanks.
Yeah.
Okay. I think next is Shri. Shri, I think you can unmute yourself. Yeah, go for it.
Okay, thanks. Fantastic talk. You illustrate, yeah, you illustrate a thing I made. It's since I'm an observer, I have to observe. I've noticed that PhDs in radio astronomy, especially from pulsars and ISM, they go on to do great things, and you confirmed that trend. Okay, let me get on to a comment, which is, okay, you spend a lot of effort in these fibers because you don't want them to be under stress and so on. But why not consider using infrared laser free space communications, like a little telescope on your station, which can, on a gimbal, and it can communicate. It'll be a nice thing. You don't need fibers. That's very much the last century. So anyway, I urge you to consider.
Right. That's a great point. Right. So yeah, the two aspects of it. One is that we haven't considered it really properly.
Anyway, I'm just saying, consider it. It's time to get away from we really have to move on to optical and infrared comm, and this is a nice illustration.
Right.
But my question, my question is, okay, so you have this using Arecibo language, a carriage house. Now let me just be a little free with mechanics. Okay, I want to add another carriage house. Maybe I'll add two more so it's symmetrical. Okay. And one of them will have a 300 megas phased array feed, and through this phased array feed and a shaped reflector. Okay, so you can operate simultaneously. That's the beauty of having a almost spherical surface. So you can through this phased array feed and shaped reflector. I would like to conduct a 300 mega survey for pulsars, because I actually think there's a very interesting frontier, which is at exactly the opposite. Of course, look, if I could find a sub-millisecond pulse, I'll be very happy to write that single Nature paper. But I'll tell you, there's really very interesting diagnostics at the low the very large period, in fact, which may be very intimately linked with FRBs. And so I suggest FAST consider the widest field phased array feed with a shaped reflector, but working at 300 megahertz to look for exactly the opposite. Vikram, am I on or off?
You're on. D.
Okay.
Yeah, I'm just waiting for. Yeah, might have lost him again. Just give it a few.
While waiting
seconds.
for him, Greg wanted me to make some comments about something about optical astronomers, which I won't.
we have time.
Right. Sorry, I guess it's just the information content of Shree's question and comment crashed in the internet. So the the suspension structure of Arecibo is much heavier. It's a few thousand tons and more. It's harder. So we just have those very flexible cables. So we can only host additional instrument on that 30-ton dome.
Oh, but Lee, wait, you're not being imaginative. No, I'll build new towers and then at a lower or a higher level.
Okay.
Yeah,
okay.
Come on. I mean, this is China. You have to think big.
Okay. All right. Yeah. Then it's Then I will take that as an excellent section. But to start with, we can put a off-axis low frequency feed, or even a few of them. Just while you're doing primary science, you can take data stream of.
Anyway, I'd urge you to do that because I think everyone's doing millisecond pulsar. That's old stuff. The 10 to 50 seconds is where the action is. Okay, enough of my questions.
Yeah, thank you.
Last quick question, Joe. I'm just going to unmute you. Go for it. There we go. All yours.
Yeah, D again.
Hi, Joe.
Hey, fantastic talk. I was going to ask, have you had any conversations with the MWA team about any kind of shadow or commensal observing? Because the time delay between the two frequencies might allow, even if you can't do real-time triggering, looking for just how wide the bandwidth of either pulsar or FRB burst might be.
Yes. So we have intermittent communication with Ramesh, and but both he and I are occupied by many other things. But that's a great thing to follow up on. Unfortunately, one of his former students, Meng Yao Xue, has just got admitted into NLC as a postdoctoral fellow. So hopefully through her, maybe we can really get this off ground. But that's real. Yeah, that's a great reminder that we should. But we probably should start with crab or something just to see whether we can catch the same pulse.
All right. I think Greg is going to defer his question to a later meeting in a few minutes. But yeah, I think Mansi wanted to close us off with some logistical announcements. Mansi.
Yes, thank you. So now what we're going to do is do a virtual meet and greet with the faculty members. So I'm sorry, this is in lieu of fancy wine and cheese and a lovely dinner at the At. We can't do that. So that's why we're organizing these smaller meet and greets. So I'd like to request all the faculty to please stay on for just 15-20 minutes here. So we can virtually welcome our speaker and talk to him some more. I'm going to stop the recording at this point and the live stream. And I request the non-faculty members to please join the separate meet and greets organized for the students, postdocs, and staff. Thank you very much once again. And let's just give people a minute here to get the logistics sorted.